Dear students, in the third part of chromatography lecture, we will discuss about plane chromatography or planar chromatography. There are two kinds of chromatography techniques under the category plane chromatography. One is the paper chromatography and the second one is the thin layer chromatography. So we will see what are these techniques. So plane chromatography or planar chromatography is a chromatography technique on a plane surface rather than on a column. So in the previous classes, we were discussing about the column chromatography techniques, adsorption and partition column chromatography techniques. But here in plane chromatography or planar chromatography, we carry out the chromatography process on a plane surface rather than on a column. So that's the difference. So there are two kinds of plane chromatography, paper and thin layer. So first we will see what is paper chromatography. So in this picture, you can see the white colored stuff. That is a piece of paper, well refined paper. That is your stationary medium. Actually, the paper is not your stationary medium. So there is a liquid which is coated over this paper. So that is the stationary medium. And the mobile phase is kept in this petri dish, for example, in this picture. So the mobile phase in this case is actually going from down to up. And here you can see a line where we keep our mixture. Okay, so when the mobile phase going up due to capillary reaction, that mobile phase will carry these compounds to the upward direction. Okay, so for example, here we can see that the mixture or the components are moving upward. And at the same time, you can also see that the distance from this baseline, the distance traveled from this baseline by the different spots are different. So that's how the separation is happening. So that we will see later. So anyhow, so we have a stationary phase which is a liquid coated on a paper, and that is our stationary phase. And we have a mobile phase which is a liquid which is kept at the bottom. Now, so in paper chromatography, that is a liquid partition chromatography. Even though we use a paper, so you may feel that it is solid, but normally a liquid which is coated over the paper, it could be water as well. So that liquid is the stationary phase. So that's why the paper chromatography is a liquid. And if the stationary phase and mobile phase both are liquid, then the principle behind the separation is partition. So that's a liquid partition chromatography. So stationary phase, film of liquid, for example water, adsorbed on a paper pad usually made of highly purified cellulose. The mobile phase is another liquid percolating over it. And the principle is nothing but the partition. So successive equilibrations of the components between the stationary phase and the mobile phase. And it is a two-dimensional development because the chromatography techniques or chromatography is happening on a two-dimensional plane. So it's a two-dimensional development. Okay. So let us see what is thin layer chromatography. So thin layer chromatography is almost similar to the paper chromatography. The only difference is the stationary phase here is not a paper. Instead of that, we coat a inert solid material on a glass plate or aluminum sheet or plastic sheet, and that will act as the stationary phase. That's the only difference between paper chromatography and thin layer chromatography. So here thin layer chromatography is also a liquid partition chromatography because even though we coat a inert solid material on a glass plate or aluminum sheet or plastic sheet, the inert solid materials contains a thin layer of liquid. So that liquid acts as the stationary phase. So TLC or thin layer chromatography is also a liquid-liquid partition chromatography. However, in rare cases, a solid could be a stationary phase in thin layer chromatography as well. Okay, so the stationary phase is a film of liquid, for example water, adsorbed on a uniform thin layer of an adsorbent like silica gel, alumina or cellulose coated on a glass or a plastic plate. Mobile phase again is suitable solvent immiscible with the stationary phase which is percolating over it. So that's the thin layer chromatographic technique. And the principle is the differential partitioning of components between the two immiscible liquids. So here you can see that this white colored part is an inert solid which is supported on a glass slide or plastic sheet or aluminum sheet, and there will be a thin layer of liquid which is coated on this inert material, which we cannot see it, and which is placed inside a beaker, for example here, and this is your mobile phase, which is a liquid, and here this port is the place where we keep our component, and when the mobile phase going up, it will carry the components as well. Here you can see that we place only one spot, but here you can see two spots. That means the components getting separated when the mobile phase take the components to the upward direction. Okay. Now, most important factor or most important thing which we have to see in a plane chromatography is the retention factor or RF value, retention factor. So let's see what's retention factor. So retention factor RF is distance traveled by the component from the original line divided by the distance traveled by the solvent front from the origin line in the same time. So it's nothing but when we place a mixture as a spot on a reference line, and when the plane chromatography is happening, the mobile phase will take your components to the upward direction. Okay. So after a particular time, the different components in your mixtures travel different distance from the reference line. Okay. So you measure the distance traveled by your each component from the reference line and divided that distance by the distance traveled by the solvent front. So always your mobile phase will be at the front. So the maximum distance travel will be your mobile phase. So if you divide the distance traveled by your component divided by the distance traveled by the solvent front, that gives you the retention factor. So if you see from this figure, so this is a plane chromatographic representation. This is the reference line, and you keep your mobile phase here, and when the mobile phase moves upward, it will carry your components as well. Okay, so here you can see that this is the solvent front, so distance traveled by the solvent. Okay, so from here up to here, the solvents traveled after a particular time, and your components also traveled with it, but they traveled at different distances. So for example, here you can see that the yellow spot traveled the smallest distance, and this one traveled the maximum, and other two spots traveled some other distances. Okay, so for example, if you take the red spot, the RF value of this red spot is the distance traveled by the red spot from here to here, okay, divided by the distance traveled by your solvent front. So here, so if you divide this distance with this distance, that will give you the RF value of this red spot. Okay, so that is the retention factor. So what is the importance of retention factor? The retention factor is very important because if you conduct a plane chromatography in several times, if you conduct the chromatography in same manner for several times, the same compound will travel same distance. So RF factor is something like a characteristic of a compound. So for example, if you conduct this thin layer chromatography, this red spot will travel the same distance if you keep all the experimental conditions same. Okay, so that is characteristic of a compound. So that will help you to identify the components in your mixture. So RF value is very important. Okay, so this is a diagrammatic representation of the plane chromatography conducted in plant pigments. So here, this is a paper strip which is kept suspended, and this end is touched in the mobile phase here, and somewhere here they place a drop of the plant pigments mixture, and when the mobile phase go up, that will carry the components as well. So here you can see that it's a green line, blue line, yellow line, red line. So 1, 2, 3, 4 components. Okay, so 4 components got separated, and they measured the distance from the reference line and divided that distance with the distance traveled by the solvent friend. They got RF value for different components. So for example, in this particular case, chlorophyll B has an RF value of 0.45. Chlorophyll A has an RF value of 0.65. Xanthophyll 0.71 and carotene 0.95. Okay, so one thing you have to keep in mind is why chlorophyll B has a RF value of 0.45, because the distance traveled by the chlorophyll B is the smallest among the other pigments. So why chlorophyll B traveled a small distance? Because chlorophyll B interact with your stationary phase more, and the chlorophyll B interact the most among the other pigments. So because of that interaction, its movement got retarded. So here carotene, if you take carotene travel the maximum distance. So that means among these plant pigments, carotene has the weakest interaction or least interaction with the stationary phase. So the carotene prefer to remain in the mobile phase most of the time. So that's why carotene travel the maximum distance, almost is travel the same distance as the solvent friend. Okay, so this RF value for these plant pigments will be the same if you conduct this chromatography in similar condition. So you will get the same RF value for these components. Okay, so RF value is something characteristic of each compound. So that's very important. And if your components are colored, so definitely you can see different colored spot when you conduct the thin layer chromatography or paper chromatography. Suppose if your compounds are not colored, then you have to develop the spot. So there are different techniques to develop spots after conducting the plane chromatography. So you can spray ninhydrin, which we normally use to color the spots, or there are some other techniques. So you don't have to worry now, but anyhow, you can measure the distance traveled by these components by measuring the distance between the reference line and the center of the spot. Okay, and divided that by the distance traveled by the solvent front. So that will give you the RF value. So RF value is characteristic of a component. Now, if you see what are the applications of paper chromatography and thin layer chromatography, so we can use these techniques for the separation and identification of compounds in trace quantities. That is very important. So you need a small drop. So the amount of mixture what you need is very, 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 very small. So in microgram level. Then separation of closely related chemicals. You can separate closely related chemicals by using this technique. Then instant purity analyzing techniques of organic chemicals. So that means if you conduct an organic reaction and if you want to know the products, how many products are formed or all the reactants are converted to products, you conduct the plane chromatography, paper chromatography or thin layer chromatography instantly. So you take a drop of reaction mixture, spot it on the paper or thin layer, then conduct the chromatography. Suppose if you have only one reactant and after a particular time, if you get two spots, that means one product is formed. And if you get three spots, that means one product could be of reactant and the other two could be of your products. So how you can determine which spot is reactant and which spots are product? That you can also conduct the plane chromatography of your reactant and measure the RF value. And next time you conduct the plane chromatography of your reaction mixture, and if there is a spot which has the same RF value of your reactant, so that means your reaction mixture still contains your reactant. Okay, so similarly, you can determine whether the reaction is completed or how many products are formed. So all those kind of stuff you can get instantly. Okay, so that's instant purity analyzing technique. Used in quality assurance in food industry, pharmaceutical industry, and cosmetics. You can also use these techniques for detection of drugs and dopes in animals and humans. Okay, so this is all about the plane chromatography or planar chromatography. So thanks for listening to the lecture.